Hello, I'm going to be talking about problem 6, the last problem in set 13. This is a driven damped oscillator. And here's a physical situation. I have a mass on a spring here, and I can, let's see if I can, if I just let it go up and down, you see it oscillates up and down. It has some damping, but it's underdamped. Quite a bit more damp than the slinky one we had yesterday, as previously. And I can also give it a force, an applied force by moving the top up and down. If I move the top up and down, I actually get a pseudo force in the accelerating frame of the pivot there. Let's not worry about that too much. But you notice that if I move it up and down at pretty much like the natural frequency, I get a big oscillation. If I go really fast, it just kind of stays put. If I go slowly, it kind of stays put as well relative to the top. Okay, so here's the situation. I've got a mass hanging from a spring, okay, and the top where the spring is attached is oscillating up and down a bit. K is the spring constant, M is the mass. Then I've also got a friction, so I don't really have to I don't have to have some physical mechanism for friction, but we often talk about a dash pot. So I've got this little arm coming out and this little paddle sitting in water, and as the mass goes up and down, this little paddle goes through the water. It's called a dash pot. That gives a friction to here. But there's friction built into any real system. All right, so here's the equation, my double prime plus cy prime, and they're using C where I used gamma the other day. That's not my C, that's what I called gamma before, but plus ky equals F of t. I've got an applied force, okay? And then I have initial conditions. The initial position is 0, initial velocity is 0. And actually relative to if this thing is moving up and down, actually the y is going to be measured relative to the moving equilibrium up and down. So y is the position in the accelerating frame of this roof. But you don't have to know any of that stuff. If you know physics, that's kind of cool. There's a pseudo force, but let's just think about the equations. Okay, there's a math course. All right, so this models a motion of a spring mass dash pot system initially at rest and subject to an applied force F of t. Okay, the unit of force is newtons. Okay, we're going to use capital N for newtons, although the SI abbreviation is really small n, but I think big N makes more sense intuitively. The mass is 0.25 kilograms. Actually, this is 0.25 kilograms, 250 grams. Okay, and then the spring, the damping constant is 0.5 kilograms per second. We can think about units. Everything in this has units of kilograms meters per second squared. So that's what units of C has got to be. K is newtons per meter. It is 25.25 newtons per meter, and the force on this is 0.10025, wow, times cos 10t newtons. Okay, your numbers are going to be different in your Weber problem. But the question is, solve the initial value problem, find y of t equals, and then for large positive values of t, what is yt going to equal? Approximately. That's the question. Okay, so the first thing we're going to do here is plug in the numbers and get the equation. Okay, so we get 0.25 y double prime plus 0.5 y prime plus K is 25, 25.25, K is 25.25. Okay, and that's y times y. And that equals this 0.10025 times cos of 10t. All right. So I'm going to take this thing and multiply through by 4. Okay? So in fact, let's get this. Okay? So here, if I multiply through by 4, I get y double prime plus 2y prime. And then when I multiply that by 4, that gives me 100, and that gives me 1. This is plus 101 y is equal to, multiply this by 4, I get 0.401 cos of 10t. Okay. Oh, I'll write this down. I just erased it, but the initial conditions are y is 0, and y prime is 0, 0. Okay, so now we can just get rid of everything, really. And our answer is going to be in meters. Y is going to be measured in meters. T is measured in seconds. They didn't put the M in for meters in the web work, but that's what it means. Okay, so what's our procedure? Step 1. Okay, find YH. Okay, the solution to y double prime plus 2y prime plus 100y equals 0. Okay, and then that will involve C1 and C2, right? Okay. Step 2, we're going to find YP. Okay. All right, one solution to the non-homogeneous guy. Okay, and this is, we'll get into more later. This will have the undetermined coefficients. We'll talk about that after we've done the YH. But one of the things you notice is that that YH goes to 0 as t goes to infinity. Right? When t is large, because there is damping here, the solution to this homogeneous equation will go to 0. So the general solution, which is y equals YH plus YP, okay, this just approaches YP for large t. Because that goes to 0. So in fact, we want to do it in this order, but before you start doing step 3, we can definitely check that we got the YP correct, because what we're going to put in here is YP of t. Right? If we wait a long time, for this problem at least, the homogeneous solution always decays to 0, and we're just left with a particular solution, also called the steady state solution, or the asymptotic solution, or whatever you want to call it. I kind of like steady state. It's not an equilibrium because it's still moving up and down, but all right. And then step 3. All right. Okay, use the initial conditions to get equations for C1 and C2. Okay. In the general solution, which is y is y p plus YH. So YH has those constants C1 and C2. So I'm going to get those two equations for C1 and C2, solve for them, and substitute back in. Okay? All right. So we can pretty much get rid of everything. So that's when I do that final solution y to the initial value problem, that's going to go here, right? All right, so let's go. Let's start with step 1. All right, there's the equation. R squared plus 2r plus 101 equals 0 is the characteristic equation, right? Now you can throw this into the quadratic formula, but remember, like completing the square is often nice, and even with your numbers, it might be kind of nice. If I write this as r squared plus 2r plus 1 plus 101 equals 0, that's a perfect square. R plus 1 all squared plus 100, oops, that wasn't right. I added plus 100 is 0, right? So R plus 1 squared is minus 100. R plus 1 is, well, square root of a negative 100 is plus or minus 10i, right? So you get R is minus 1 plus or minus 10i. Okay. And if you get fractions here in your web work problem, you have different numbers than I do, but you screwed up if you got fractions, so check your algebra. So we get YH is C1 e to the minus t, 1 times t, times cos 10t, plus C2 e to the minus t sine 10t. And I kind of like this as factoring out the e to the minus t times C1 cos 10t plus C2 sine 10t. Okay, so I have to, if I type this in, I've got to write the e to the minus t only once. Okay. So that's step 1 done. Cool. A third of the way through. Okay, step 2. Okay, yp, all right, so then since the right-hand side is a constant times cosine 10t, yp is going to be a times cosine 10t plus b times sine of 10t. That's like the rule 1 thing, right? The right-hand side is cosine of 10t. You need cosine and sine in general. And do I have to modify this? Well, you might think I do because there's a cos 10t here and a cos 10t here, right? But e to the minus t times cos 10t is not the same as cos 10t, right? So I don't actually have to modify this, right? Cool, which is nice. So let's do the derivatives. So now what I do is this is a and b are the undetermined coefficients. I'm going to plug this yp into this differential equation and solve for a and b that make it work. Okay? So let's do the derivative. What is yp prime? Okay. Minus 10a sine of 10t, because the derivative of cosine is negative sine, and then times 10 from the chain rule. Then I get plus 10b cos of 10t. Right? And then I get yp double prime. And then differentiate again. Derivative of sine is plus cosine. So I get minus 100a cos of 10t. And then I get plus, oops, another minus, derivative of cosine is negative sine, minus 100b sine of 10t. Okay? And now what I'm going to do is I'm going to take yp double prime plus 2yp prime plus 101 yp. And then I'm going to figure out what that is and set it equal to 0.401 cos t. Okay. Now I'm gonna write it as something. Let's write it this way. I'm gonna write it as cos of 10t times something plus sine of 10t times something else. I'm gonna gather the terms. Okay, so if I take y double prime plus 2yp prime 101y, what do I have from the cosine? Well, the cosine, I get an a here from the yp double prime. 2yp prime, I get a 20b times cosine, right? Okay, and then I have 101. Sorry, I screwed up on the yp double prime. Okay, yp double prime, sorry, has a minus 100a. Sorry, minus 108 cos 10t plus 2yp prime. That was right here. This is plus 10b times cos 10t, which I factored out. And then I have plus 101 yp, so I have plus 101a. That's 101 times yp. And I close that up. And now what do I get in front of the sine 10t? From the yp double prime, I get minus 100b times sine 10t. Then I get plus 2y prime. I get minus 20a. Oh, by the way, I screwed up before. That's a 20. The 2b gives me, the 2yp prime gives me 2 times 10b, that's 20b. Okay, watch me like a hawk here. Okay, then I also have plus 101 times yp, that's the b. Okay, and I'm going to set that equal to 0.401 times cos t plus 0 sine 10t. I don't see it, so there's actually a 0 there. Okay? You with me? All right, so we can get rid of this. Let's get our two equations and the two unknowns. Two equations and the two unknowns, A and B. The coefficient in front of cosine 10t has got to be the same on both sides. And minus 100a plus 101a is just a, right? A plus 20b, that I want to set equal to 0.401. Okay, that's coefficient in front of cosine for 10t on both sides. What's in front of sine? I get b minus 20a, and that is 0. Okay. So here's our system of two equations and two unknowns, A and B. So I want to solve. Okay. Well, let's start with this guy here. B is 20A, right? And if B is 20A, I can plug it into here. I get A plus 20 times 20A equals 0.401. That 20 times 20 is 400. This is A plus 400A is 0.401, or 401A is 0.401. A is, well, what is that? 10 to the minus 2, right? That's 10 to the minus 3, I think. Yeah, it's 10 to the minus 3. Good. And what is B? Well, B is 20 times 10 to the minus 3. 20 times A is 20 times 10 to the minus 3. That's called 2 times 10 to the minus. Okay, well, let's stop working. Okay, we're back. I don't know what happened. And we're still recording. I don't know if I'm going to be able to do this. All right. Okay. So that's what YP is. I'm not sure how long it's been freaking out, but maybe our internet connection. How you guys? Let me know if how your internet connection is doing. Actually, I'm kind of curious. But anyway, so let's remember this is all in meters. So this is actually 2 centimeters, right? And this is 1 millimeter. 10 to the minus 3 meters is 1 millimeter. So this is, I chose these numbers to make it work kind of for this one. As I do this thing, it's going up and down, up about 2 centimeters and down about 2 centimeters as I shake it. Okay, and then your numbers might be kind of weird, like it's going up and down like 3 meters or something, who knows. All right, so that problem was not written by a physicist, it was written by a mathematician, I'm sure. All right, so we can get rid of all of this. We got YP, we also have the YH. So I think we've done step 2. And by the way, what you should definitely do now before you move on to step 3 is plug this answer into the second question in the web work. And if that's not right, you better fix it before you go on to step 3, right? So the second question is just asking for YP. Okay, the particular solution after the homogeneous part decays to 0. All right, so step 3, we're going to impose those initial conditions. So remember that we want y of 0, which is yp of 0 plus yp prime of 0. We want to set that equal to 0. And we want y prime of 0, which is yp prime of 0. Oops. This is plus yh of 0. That's 0. Y of 0 is yp, y is yp plus yh. So y prime of 0 is yp prime of 0 plus yh prime of 0. And I'm going to set that equal to 0 as well. So I'm going to have the constants C1 and C2 in this when I'm all done. But let's compute what yp of 0 is and yp prime of 0 is. Well, we have yp of 0 is just 10 to the minus 3, right? Plus something times 0, okay? We'll think about yh of 0 later. Let's get yp prime of 0. Yp prime of anything is 10 times 10 to the minus 3 times sine of 10t with a minus sign. Okay, and that then plus 2 times 10 to the minus 1 times cos 10t. So I use derivative of sine as cosine, use the factor of 10 from the chain rule. So now I can get what yp prime of 0 is. That sine of 0 is 0. This is just, that's 1, so I just get 0.2. 2 times 10 to the minus 1, right? Now let's get YH and YH prime. Remember that YH is e to the minus t times C1 cos of 10t plus C2 sine of 10t. So YH of 0, what is YH of 0? Well, that's 1 when t is 0, that's 1, that's just C1. Right, plus 0. YH prime of any t is, well, I'd have to use the product rule, right? And this is kind of nice to factor out the e to the minus t first for this. I get minus e to the minus t, derivative of the first times the second, C1 cos 10t plus C2 sine of 10t. And then I have plus the first, e to the minus t, times the derivative of the second. Derivative of cosine is minus sine, so I get minus 10 from the chain rule, times C1 sine of 10t, plus 10C2 cos of 10t. Okay, so now I can actually compute y h prime of 0. Okay, when I evaluate this, 0, again, e to the 0 is 1, cos 0 is 1, sine 0 is 0. I get minus C1, that goes away, plus 10C2. Okay? All right. So that looks familiar. Of course, I did this before because I didn't want to mess up. So what are these equations become? Yp is 10 to the minus 3 plus yh of 0 C1, and I'm going to set that equal to 0. Okay? And then what is yp prime of 0? That's 0.2 plus yh prime of 0, that's minus C1 plus 10C2, and that should be 0 as well. So here's our two equations and two unknowns for C1 and C2. And as you can see, our systems of equations are pretty easy in this one. Here, what do we get here? Well, this one's kind of easy. C1 is minus 10 to the minus 3. And then this one says 0.2 minus negative 10 to the minus 3, plugging in the negative 10 to the minus 6 for C1, plus 10C2, that's 0. Okay? So what's this going to be? I'm taking 0.2 and I'm adding 10 to the minus 3. I get, first, well, C1 we got, right? And now we're looking for C2. This combined gives me 0.201, 10 to the minus 3, plus 10C2 equals 0. So C2 is negative 0.201 over 10. Let's put it up here. C2 is, that's 10. This is negative 2.01 times 10. That was 10 to the minus 1, and now it becomes 10 to the minus 2. Okay. So we got C1 and C2 in this, is it still written anywhere? In our YH form. I don't see YH anywhere, but we remember what it is. All right, so finally, the solution is, plug that back into, okay, we got the YP. Remember that Y is YP plus YH. So since we got YP there, let's write this as Y of T is equal to YP plus YH. And what is YH? We got the constant. So this is e to the minus t times, okay, minus 10 to the minus 3 cos 10t. Okay. And I get minus 2.01 times 10 to the minus 2 sine of, can't see that very well. Sine of 10t. All right. And that's all in meters. All right. Wow. So this is YP plus YH with the constant chosen. And I've actually got this plotted out. Let's share the screen. I've got a Mathematica notebook. that will actually allow me to check my answer. All right, so what did I get before with yp? My yp was 10 to the minus 3 cos 10t plus 2 times 10 to the minus 2 sine 10t. That's right. And if I actually computed yp double prime plus 2yp prime, 101y3, and lo and behold, I get 0.401 cos 10t plus something times 10 to the minus 7, that's a 0, right? So I got, when I plug in yp for this, I satisfied the equation. Okay, and then for the solution to the initial value problem, yivp, I call it here, I take yp plus yh. And the yh should be just like what I wrote before, minus 10 to the minus 3 cos 10t minus 2.01 times 10 minus 2 sine 10t. That's good. And so when I simplify the whole yivp differential, left-hand side differential equation, I indeed get the right-hand side plus 10 to the minus 16 times junk, right? And then I also check the initial conditions. Y of 0 is 0, and y prime is 0 is 0. That's what so I satisfy the equation and the initial condition. So here I have some plots. So here I'm plotting y in meters versus t in seconds. So the particular solution, or the steady state solution, is in blue, and then the solution to the IVP is in red. Starts out with y equals 0, y prime is 0, and then it starts growing. And as time goes on, it grows. That was time from 0 to 2. Here I go from 2 to 4. The solution to the IVP is getting really close to the particular solution, or the steady state solution. If I go from 4 to 6, you can barely tell the difference. Okay, so there. I know this is kind of long, but it's really, if you you can do it. And I'll just say that. I'm not going to say it's going to be easy, but you can do it. All right. So hang in there. I know we've all got this coronavirus thing going on, but stay well and keep doing your classes. I know it's kind of hard to find the time. All right. Bye.